Uh, Now the next one is 20.4.2. So it's the definition is already similar to a convolution, except effect a negative sign. This is this definition of this so-called overlap integral. So you have the function psi. Obviously, this is integrating over all space. So, and define it as three-dimension space. So there is three-dimension integration. Yeah, actually, the function a psi is a. This is size of a. And that goes again. Minus a constant vector a b minus a constant vector b. Okay, so it's not exactly the convolution definition. It's not exactly in the form of the definition. So what you need to do is just do a change of variable to put it in a similar form to it, more similar form to a convolution, like you define, like in the textbook, is define this as alpine, right? Alpine is r minus a, so r is alpine plus a. So this change to alpine plus a becomes minus b minus a, right? And it's still not exactly the same because the definition is alpine and then r minus, I mean, the whatever alpine minus r, right? We go back to the definition. And 3D definition is 20.69. It's r minus alpine. So this is actually uh, uh, the negative of this one. So this is like if you define this as R, this is like the text define as R. So this is a alpine b alpine minus R, right? And dq alpine. And obviously dqr is the volume element doesn't change if you define like that, right? And um, the usual formula of I mean, definition of convolution is another function with r minus alpine. But you go back to that definition. So this is not exactly the same with a negative sign. So it's like this is we define this function as a negative, or whatever this a g function is just phi b minus r. Then this phi b alpine minus r is just uh, this g of r minus alpine, right? And then then this would be the r function. So the SAB would be hence an R. SAB. Because look at this integral. You integrate all the alpine out, the only thing left is R. Yeah. Right. And this is like the convolution, except that there's also the coefficient in front. The definition has the 1/2 pi. That 1/2 pi to the 3/2 minus 3/2 power. Right. So if you use the standard form, this will be 2 pi. A and psi B. Psi B is as it becomes G, and then this is in the R. This becomes the right, yeah. And this is a function of R because of this definition. R this becomes R minus R prime. Compare with the definition of the convolution is like that. And the reason to do something like that is to use the equation, the formula that we derive. That is 20.72. With this, I said, so this is by equation 20.72. This is the left-hand side of that equation, right? Because it's just the integration. So this shows that SAB is equals to, now it's just the Fourier transform of these two functions. So it's phi A Fourier transform. That's the function of K. And then obviously is also for G Fourier transform also as a function of K. Wait, that is just applying the formula. And the final step is that because we define G as changing the argument, basically the negative argument, then you use one of the property of the Fourier transform that we derive. I think that is the beginning of 20.3. Yeah, that is 20.50. So by 20.50, this function is defined as another function with changing the argument to negative sign, just like the 20.50. The Fourier transform just changed the argument to minus K. This becomes going back to phi B, thinking that is phi of B Fourier transform, but with a negative K. Okay, so that's just the complication because of this definition. So you introduce with minus K in this formula. And that is the general formula. Yeah, I missed that. I missed it. A factor in the formula. The formula 20.70 has an e to the minus ik that on the right hand side is factor. Okay. And for us is R is capital R. This is okay.
Is that leftmost point of the ball supposed to also be phi B or should it be phi A?
This is yeah, phi A. This is phi A. Because there are two functions, how can the overlap of two functions? Except that I mean this is the formula. This is the formula on the bottom of page 989. It's exactly the same formula. Okay, and the rest is just using a one example. I mean, example of this formula. Just use a simple phi. I mean, this is general, so whatever phi A and phi B, you define an overlap this way. In Fourier transform, you can calculate that in this formula. But that's just the straightforward property of convolution. The rest is a so in order to proceed These are general formulas. So if you choose both phi A and phi B equals to, so if you use phi A equals to phi B equals to e to the minus CL. I say the R, the and it's real because then I forgot all the compound. There's a complex function. I also forgot, but yeah, forgot it. And then yeah, this also this is a convolution between the complex conjugate phi A and phi B, which is I mean and G, which is defined as this one related to phi G, right? And now you basically get rid of all these the label A and B are the same, and then the complex conjugate is the same. So this becomes simple. And Fourier transform of this one, the exponential function, we did that in, I think, in section 2. We did that. I mean, the rest is just calculation. It's not very interesting, actually. Yeah, let's just look that up. Where is this exponential function? Where did we do it? Oh, yeah. The 20 point example, 20.2.1. Right. This is exponential function and get the, the full transform. Just by that example, the final result is this one, except that we need to translate all the formula. Oh, wait. That is just, this is 3D. So it's a little different. It's not that, it's, we could go to the 3D, transform the 3D. Yeah, that is actually 20.44. 1D we did that. I mean, this is the radial coordinate of the spherical coordinate. So it's 3D. This is 20, equation 20.44. So phi is either phi A or phi B. The transform is 1 over this vector. There's an 8 pi vector, 8 pi, and the z is a theta, and k squared, theta square. Okay, and now you can substitute this into both here and there because now A and B are the same, and complex conjugate is the same, and the final result is just a complicated. It's not very complicated. It's just an integral that can be evaluated. Some, that is the integral. I mean, in your textbook, just with all these factors. Data is a constant, so it's not involved in the integral. What is involved is this factor with a k, I k dot r, and all these with a k in the denominator. Data squared factor 4, because you have two of these, so you have factor 4. Okay, and that is the integral. The textbook did evaluate that using whatever the spherical Bessel function is basically expanding this exponential function using spherical Bessel function, which we obviously haven't gone to Bessel functions chapter, but once we learn the complex integration, this can be done using complex integral method. It's not too difficult, but it will take about 30 minutes to do that. So I in the previous class I make a video of that one. So if you like how you evaluate that, how you learn how to evaluate that kind of thing. I have a video on my YouTube channel. If you like to evaluate that, but yeah, it's just long. It's nothing special. And the final result is 20.82. After you evaluate this integral and do some rearrangement, you get 20.82. Okay. Yeah. Why what? This one? This one? This one? Define what? Because its standard form is this is not the standard form. The standard form is I already quoted that to you. The standard form of the definition of the convolution is for 3D is 20.69. So this is kind of space the way the standard form of between two functions f and g in 3D. The standard form is this g in r and f and r minus r prime. And after you integrate r prime, this becomes a function of r, right? Because the only other variable left after you integrate r prime becomes function r. So that's the definition. And you look at this one, after we do this change of variable, it's still not this form because it's alpine minus something. This is something minus alpine. Okay, so you need to redefine your function. It's not exactly from 5b. You define a function g, which is 5b, but evaluate as a negative position. Basically, just changing the argument to a negative sign. Yeah. What's the equation number again for the form? This is 20.16. Right? This is just after we discussed the 1D convolution, or one variable convolution, we just generalize that to 3D, exactly the same way. Just like we have 1D Fourier transform, we get the 3D Fourier transform. Yeah, yeah. This is defined as R minus R prime with this function G, F, and G. Go into the definition. But this is G. Well, this is 5B, right? The 5B, the argument is R prime minus R, not exactly as this. So you need to define the G like that. This becomes, so this one is equals to G R minus R prime. Now this is the same as this one, right? This is just mathematics. Sometimes it's just pattern matching. You define something like that, then you want your equation or your expression match to what you define, right? You define a convolution like that, and so you try to manipulate your expression such that your expression match back to your definition. Okay, and the reason to do that is once you did that, you can use the formula that we derived based on this definition. Otherwise, if you just apply it arbitrarily without really matching the definition, you make some error, some error in sign or whatever factor, right? So the only thing I did that is just going back to the standard definition. I don't get your question. Sorry. Yeah, this is the definition. Just I redefine. I introduce a function just so that I can write it in the standard form. Yeah. Then that this becomes a convolution, become files of A and G. Okay, using this definition, right? Then I can use the formula that you integrate this two, which is just this one, is equals to the multiply the we transform and this factor, that's the exponential factor, and integrate in case space. That is just the formula that we derived before. And the last step is using back this definition and use the property of Fourier transform and going back to the Fourier transform of phi sub b and then change the argument from k to minus k. That's just a property of Fourier transform. That we derive, we also derive that. Okay, and finally you get this formula. Okay, I mean I'm doing it in details. Yeah.
So that question is very important. Like now, if I replace again,
yeah.
Why not just to replace the top so that it looks
yeah, that is just to say some repeating argument. If we don't have to introduce that convolution, we actually can get rid of all the uh, discussion of convolution. Forget about convolution. It just apply Fourier transform. Just like what you said. I just forget about everything and just do Fourier transform of this of both of these and get to this one. That is possible. But that will repeat some of the argument that we did before. So we introduce a convolution so that we devise some formula so that we don't need to repeat all this the derivation every time. And then we just apply the formula. Do you understand? We could do that. We could definitely do that. Just basically just turning the crank again. Right?